Right, now we're going to look at the Lrc series circuit. Previously, when we looked at the LC circuit, we assumed that there was no resistance in the circuit. This, of course, was an idealization. Of course, every real inductor has resistance in its windings, and there may also be resistance in the connecting wires. Because of resistance, the electromagnetic energy in the circuit is dissipated and converted to other forms, such as heat. Suppose an inductor with inductance L and a resistor of resistance R are connected in series across the terminals of a charged capacitor, forming what's called an Lrc series circuit. So we've got this set up here. As before, the capacitor starts to discharge as soon as the circuit is completed, but because of I2I losses in the resistor, the magnetic field energy acquired by the inductor when the capacitor is completely discharged is less than the original electric field energy of the capacitor. In the same way, the energy of the capacitor when the magnetic field has decreased to zero is still smaller, and so on and so on. So you can see that you end up with this happening. Every time an oscillation occurs, the R will dissipate a bit of energy. The next oscillation, it'll dissipate a bit more. If the resistance R is relatively small, the circuit still oscillates, but with damped harmonic motion, as I've just described. And we say that the circuit is underdamped, so we call that the underdamped condition. If we increase R, the oscillations die out more rapidly. When R reaches a certain value, the circuit no longer oscillates, and then we say it's critically damped. So at this point, here it wasn't quite damped, so it's underdamped. Now it's critically damped. For still larger values of R, the circuit is then known as overdamped, and the capacitor charge approaches zero even more slowly. So we've got the three conditions here. We've got underdamped, critically damped, and overdamped. We're going to analyse this, a function to describe this, the derivation of it. We're just going to skip and just give you the solution and then just prove that the solution fits. We'll end up with a second order differential equation basically, but we're going to give you the solution, then you can differentiate and see that it fits the differential equation, then you know that it's true. The important thing is to get a physical feel of what the equation is saying. So that's the important point here. It doesn't matter that you can't solve the second order differential equation, it doesn't matter. So anyway, let's just go through the analysis of this. To analyse an Lrc series circuit behaviour in detail, we consider this circuit. So we're going to look at this circuit here now. It is similar to the LC circuit except for the added resistor R. We also show the source that charges the capacitor initially. So here's the source, EMF, the source of EMF, and that's going to be charging the capacitor. First we close this switch. The switch is now closed, and the EMF is going to charge up the capacitor. When we throw the switch back over to here, this circuit will be activated, and we're going to, the time we flick that switch, we're going to say that is t equals 0. So I'll just read it anyway. Then at time t equals 0, we flip the switch to the downward position, removing the source from the circuit and placing the capacitor in series with the resistor and the inductor. So now we've got all of these in series within one circuit. To find how Q and I vary with time, we apply Kirchoff's voltage loop rule, starting at point A and going around a loop in direction A, B, C, D. That becomes minus IR, minus L di by dt, minus QC equals 0. I could have gone the other way round and just end up with them all being positive. What we're going to do is differentiate that, and we'll rearrange it. And remember that dq by dt this time equals I. We end up with this equation. This is a second order differential equation. There are general methods for obtaining solutions to this. The form of the solution is different for the underdamped and overdamped cases. The general form of the solution is as follows, where A and phi are constants. Just looking at this function alone, if we take the first and second derivatives of that and plug them back into all of these terms, and you find that equals 0, you know that that's a solution. There's no need to actually solve this. If you've got the solution, you plug it in, then you know that's going to satisfy this, and that's all we're after. We just need a function that's going to be able to describe Q as a function of t and I as a function of t, and because we know it, there's no need for you to sit there and find the solution to this second order differential equation. There's no need to. The solution this solution here corresponds to the underdamped behaviour shown in figure A. This is the amplitude part, and you can see it's over time it's getting smaller and smaller, and it's multiplied by this sinusoidal function cosine. Obviously that produces this form here. So that nicely describes how the energy is dissipating in this LRC series circuit. One thing to note is this term in the exponential factor r equals 2L is not the same as the factor we had analysed with the RL circuit. In the RL circuit it was just R over L. So you can see here that this damping is much stronger. It's R over 2L, not R over L, so don't get confused by that. If R equals 0, you get e to the minus 0. That basically just goes to 1, and you end up with A cosine, and this term disappears. You end up with Q being A cosine 1 over LC. If you differentiate Q, you get I, so you get sine. You can tell that will actually become what we had for the LC circuit, which was I equals I naught sine WT ad theta. It means that for R equals 0, you end up with the LC condition. That's really what I'm trying to say. If R is not 0, the angular frequency of the oscillation is then less than 1 over LC. You can see it here. When R squared equals 4L over C, we have critical damping, and that's because that's the term under the square root is going to be equal to 0, so we get this condition here. And for even larger values of R, we have overdamping. So this equation describes all these three conditions. So that's really a quick summary of the LRC series circuit. The practical applications emerge when we include a sinusoidal varying source of EMF in the circuit. Such a circuit is called an alternating current AC circuit. The analysis of AC circuits is our next principal topic.